So we have defined the Riemannian manifold, which is a manifold with a metric, positive definite section of this symmetric space. And with the metric we can define new entities and new operations. So we have orthonormalized it, and EI is the basis, such that the metric on that basis is delta ij. Then we define the derivative of the metric, basically, which is this complicated operation. And a connection is compatible with the metric when this derivative is identically zero. We have seen that in a Riemannian manifold there exists only one torsionless connection that is compatible with the metric, which solves these two conditions, and the solution is what you know as Levi-Civita connection. And then we started working out the formulas in the basis EI, where, as we said, the metric is delta ij. So first we define coefficients b, I, j, k, knowing that the derivative del ei, ej must be a combination of the same ek, or the ek's, any base, and the commutator is a vector field, so that's also a combination of those, and the coefficients are a, I, j, k. And then we study the conditions of torsionlessness and del j equals 0, and see what they look like in this basis. Torsion equals 0 gives a relation between A and B. And now let's move to the other condition, del G equals 0. So del G is the object defined here. And we have to compute it on EI, EJ, EK. Now let's see what happens when we do that. So, okay, X is EI. Y is EJ. And Z is EK. So G on the elements of the basis, which means the metric contracted on the EI, EJ, EK, is by construction delta JK. So the first contribution is 0 because it's a vector, a derivation on a constant. And in the other cases, we just apply the definitions here, which introduce these coefficients B. So we remain with minus G of B, not gamma, it's called B, E, J, K, let's say L or M, EM, EK, minus G of EJ, and then B, I, K, M, EM. Now this is simple because this is the metric contracted with these two vectors, and we have these coefficients. They go out because the contraction is a multiplication. There are no derivatives here. And G, we remain with G of EM EK, which is a delta of MK, same delta. So you have minus B IJM delta MK minus B IKM delta MJ. And that's it. That's a condition on the coefficients. Basically, it says that in these two coefficients, in these two indices, which must be raised and lowered, but let's not do it, the matrix B is antisymmetric. In physics, we will have instead of eta, we will have delta. We have eta. So I just anticipate what we will get there. We will get what we call condition on a spin connection, and that will be an object like that, which will be antisymmetric in two indices, but we will see it probably in 2 days or something. We will start moving to the physics notation today also, I think. But for the moment, let's end the part of differential geometry. Let's introduce the Riemann tensor again. Because now we have the metric, so we can play with it, and we can define a tensor like this, acting on 4 vector fields and giving a smooth function. That's the map, defined as follows. So yeah, you know that the Riemann tensor indeed has 4 indices, but if we want to define it in a way that is manifestly independent on the coordinate frame, we do not use indices or specific bases. We just use this implicit definition. That's G of R, X, Y, Z, W. And that's it. Let's recall that R of X, Y, Z was equal to del XY just a sec. Del X, not del XY, this is the torsion. Del X, del Y, Z minus del Y, del X, Z minus del, or the commutator Z. Okay, so the Riemann tensor now is defined that way. And it has some properties. It is anti-symmetric if you exchange the first two. Or the second two. And it is symmetric if you exchange the first pair with the second pair. So again, this I leave to you as an exercise. To prove these. And the Bianchi identity also is an exercise. The Bianchi identity looks like this. Where del R is a map that acts on 5 vector fields and is defined as follows. Let's take the first vector field and make it act on the function obtained by taking R on the other 4. And then you have minus R acting on del x, y, and the other 3. Minus R acting on y, del x, z, and the others, and so on. So del x in turn acts on y, z, t, and w. You have 4 terms, and you subtract them all. Minus R, y, z, del x, t, w, minus R, y, z, t, del x, w. So again, this is an exercise, and in the exercise you have to highlight if and where where you need to use t equals 0, the condition of being the metric, the connection torsionless, and the metric compatibility. If and I presume you need those because we wrote the other time the Bianchi identities in general, and there was the need to have a torsion, vanishing torsion, to have 0 on the right hand side. Otherwise you have many more terms. But here you have also the metric around, because we have defined the metric, the Riemann tensor, this way, so presumably you will also need to use the metric compatibility, but you have to find out. So this is the exercise. Now, Ricci tensor. The Ricci tensor is a contraction of the Riemann tensor we have just defined. So you take the Riemann tensor and you act on x, ei, y, ei, and sum over I. That's it. And then you have the scalar curvature R, which is a further contraction of the Ricci tensor. We will not enter into details here because we will see them again in the physics part. So, but to conclude the part of differential geometry before moving to Lorentzian manifolds, let's also talk about a few other concepts that have some use, and in particular, what is a Lie derivative. And to define that, we need what is called interior product, or contraction. We define the exterior product of differential forms. Now we define the interior product. What is it? Let V denote a vector field, and omega a K form. Then the contraction of V with omega is denoted by this I V omega. That is a form of degree k minus 1. And that is the form, so since it is a form, it acts on vector fields k minus 1 vector fields. So it's the form that, acting on k minus 1 vector fields, give the same that you obtain by acting by means of omega acting on V and the other k minus 1 vector fields. For example, in local coordinates, so we have omega equal to something like omega A1 AK dx A1 dx IK. And the wedge is understood. Then IV omega is obtained by contracting VI with the first index. The other indices are left free. So you have a k minus 1 form, and actually, since you can contract in k different ways, you multiply by k. That takes care of the 1 over k factorial and 1 over k minus 1 factorial that you have in the other notation. So if you want to, if we insist with this notation for the forms, then you have this k. The Lie derivative is defined as follows. Again, V is a vector field. And omega is a form of some degree. Then the Lie derivative of the form is this: the exterior derivative of the contraction plus the contraction of the exterior derivative. So if you have a k form, the Lie derivative is a k form, because you lower the degree by 1 unit by means of the contraction, and then you raise the degree by 1 unit by means of the exterior derivative. And here you do the contrary. First you raise the degree by 1 unit by means of the exterior derivative, and then you lower it by 1 unit. So the Lie derivative returns a form of the same degree. So you can also write schematically div plus ivd. So let's see some examples of Lie derivatives, and then we will see more precisely the geometric meaning. So omega equals a zero form, which means a function. Then LV of f is what? The first thing doesn't contribute, because IV would have to return a -1 form. You cannot lower the degree of a zero form, so you just have EV df, and that is EV dxi df over d partial f partial xi, and when you contract, that is just this, namely the derivative of f along the vector field. The gradient of f multiplied by means of the scalar product with the vector. That's it. Instead, if omega is a one form, so we write omega I dxi, then let's see what happens. So first, the contraction. The contraction is just the product. If we want, we can keep the indices like that. So then we know that d omega is equal to d partial j omega I dxj dxi. Then we also know that well, we can work out the exterior derivative of this. That's the derivative of it as a function, because this is just a function. So we have partial j vi omega I dxj plus vi partial j omega I dxi. Instead, when we contract the exterior derivative of omega with v, as we know, we have to first contract with the first index. So let's see. First we contract with j, and we lose that differential. Since this is not anti-symmetrized, I don't use the formula here with k, because this is anti-symmetrized, so all contractions give the same contributions, but here I would have to do that with partial j omega I minus partial j I omega j divided by 2. But instead, I just contract with everything, knowing that when I contract with the second index, there is a minus sign, because I have to exchange the dx that's there with the dxj, dxi, dxj. So that will be omega I d partial j omega I, and then I lose the second differential, so I have this. And you see that when you sum the two, these objects cancel out. And so the Lie derivative of omega is the sum of these two things. Let me write the second one first. Vj partial j omega I plus partial j vi omega I. Here there is j. This must be j, because I have to differentiate. I is the index that's contracted, so this is xj. Yes, and indeed they match here. So if I want to collect, let's say, yes, the xi, the second one is okay. In the first one, I have to change names. So this becomes I, j, j, I. And so I have partial I Vj omega j. That is the Lie derivative. Property of the Lie derivative of the exterior product of two forms is it satisfies the Leibniz rule with no particular sign because of the special properties of the Lie derivative. So that's it. So this is an exercise. For a generic n form, where the components are completely anti-symmetric, the formula of the Lie derivative is what? Is first you differentiate the components along the vector, and then you have an additional contribution where you differentiate the vector instead. And you contract with the first index. So you take one index, the first, for example, from omega, and you put it into the partial symbol, and then you contract the index at its place with the vector. Okay. dx I1 dx In. And the derivative, the Lie derivative of a vector field, of a vector field, you can define also the Lie derivative of vector field. So if x and y are vector fields, the Lie derivative of y along x, you can say, is just the commutator. That's the definition. You can ask yourselves where does it come from. Now we will see that it comes from some more geometrical construction that is the same for all objects, both vectors and differential forms. And this is the flow of a vector field. Flow of a vector field, what is it? Let x, and in local coordinates we will write it like this, denote a vector field. And x1, xn denote a point of the manifold n. Then we can define a curve gamma from the unit interval to m, which we will write in components as phi a1 of t, phi an of t, So these are the coordinates of the point on M mapped by the curve into which the time t is mapped by the curve. And we define a curve such that as the solution of the Cauchy problem that I write here. So the initial point of the curve is the point we chose. And then we write down a first order differential equation like this. These functions of t are such that their first derivatives are equal to ai computed on the same points of the curve. So given those functions ai of x, you can define this Cauchy problem, first order differential equations with initial conditions. It will admit one and one solutions only, so that will be a curve. And if you start from another point, you will have another curve. And if you start from another point, you will have another curve, and so on and so forth. And this is what defines the flow, and every such curve is only built by means of the vector field x and its coefficients, you see, ai, and then the initial conditions you choose. So you can choose any initial condition you want. Of course, if you start from here, you will have the same solution. So this defines a flow, what is called a flow of the vector field. Now, for some manipulations that we're going to make, let's write the solution. We rewrite the solution of the system and the system itself in the following way. So we want to write phi I as functions of both t and the initial conditions. Then we rewrite the system as phi I, the initial condition will be t equals 0x, will be the initial condition. And in this case, the only difference is that now the derivative with respect to t is, of course, taken at given initial conditions, so it's a partial derivative with respect to t. And that is equal to ai phi of tx. So that is convenient. Why? Well, we'll see in a moment. Particularly, let's give a few simple properties. Well, an obvious thing is that d the partial phi I partial xj is equal to t delta ij at t equals 0, because at t equals 0 this function becomes x I. Now the Lie derivative is basically the derivative of the vector flow at time 0, the initial derivative. For example, let f be a function on the manifold. The Lie derivative Lx of f is the limit for t tending to 0 of the incremental ratio of the function f along the curve. So basically you take f, you compute it in phi tx, and you subtract f of x. So what is that? That is the derivative with respect to t. And so that is df dxi calculated in this point times the derivative of phi I with respect to t. But everything must be calculated at t equals 0. When t equals 0, this phi becomes x, and when t equals 0, d phi I partial phi of partial t, here it is, it becomes ai of x, because phi becomes x. So you have ai of x partial f partial xi of x, which is, as before, the Lie derivative, the gradient of the function f contracted with a vector that defines the flow. And the vector has components ai now in this notation. This is a small x. This is completely general, and you can do it for everything, for forms, for vectors, and it will always give what we defined previously as the Lie derivative. So maybe before stopping, we can do it for vector fields. So let y denote another vector, and then we want to compute the Lie derivative of these two objects, and now we view it as the derivative of the vector. So you take the vector and you flow it. Let's see what you get, and then you take the derivative. What does it mean to flow the vector? It means that you move along the curve, the flow, and instead of x, you will have phi, and instead of partial xi, you will have partial phi I. And then you have to take the derivative of that at t equals 0. So let's do it. Now, the derivative with respect to phi I can be written as the derivative with respect to x j times the derivative of xj with respect to phi I. And everything here is computed not in x but in phi of t and x. So we have to compute this object. So the first contribution, the derivative of bi will be partial bi, partial phi k, partial phi k, partial t. And then the rest is unchanged. Plus the derivative here, so you have bi of phi times the derivative with respect to t. That is a derivative at constant x, so we'll have this. T equals 0. Now we can compute this because this object we know that at t equals 0 is just ai of x, ak, so bi of phi becomes bi of x, and phi becomes x. At t equals 0, phi becomes x. So this derivative is just partial k bi of x this object we know becomes a delta function, so that's 1. That's the identity, and so we have partial xi. This is the first contribution to the commutator, if you remember. And then we have bi of x, because now we have bi of x. When t equals 0, phi goes to x. And then we have this thing here, which we have to work out a little bit. But I can anticipate what you get, and that is partial a partial I aj of x. So first we write it down and then we prove it. And actually with a minus, because indeed we have to obtain the commutator. And we do obtain the commutator. So what we want to prove is that this object, when t goes to 0, goes into that object. minus partial I aj. Yes. So partial squared x. Now there is bi. Yes, okay. Yes. So partial squared xj divided by partial t partial phi I equals, for t equals 0, minus partial I aj of x. And that we will do after the suspension.